All right, so now I'm going to talk about what are called characteristic curves. Or sometimes referred to as the method of characteristics. Okay. So what I'm going to do to illustrate this idea is that, so the whole point of characteristic curves are that curves along which the solution of a PDE is constant. Okay, and so it's like perhaps try to illustrate this with an example, which would then sort of also give you an idea of how it's used in the solution of PDEs. So let's consider an example. So let's consider the following. Ux plus Cuy is equal to 0. Okay. And so this is a function obviously in x and y. And let's suppose that U can be expressed as a graph. Well, actually, no. Let's suppose that U is constant along a curve in the xy plane that can be expressed as a graph. So what I mean is that y here is just some function of x. Okay, so I want that u x comma y of x, right, is constant for all x basically, right? So that means that if I differentiate this with respect to x, the total derivative with respect to x of this should vanish. Okay. So this is equal to ux plus uy dy dx. Okay. So I want this to be 0. So that tells me that the curve, right, is along which the solution is constant, satisfies this differential equation. Dy dx is equal to minus ux over uy. Okay, so let's look back at the original differential equation. So this turns out to be equal to, for that specific differential equation, c. Okay, so it turns out that for this particular differential equation, it is possible to find curves which are graphs along which the solutions are constant, and those curves are described by this equation dy dx is equal to the constant. So these are just straight lines of slope c in the xy plane. So these are just straight lines with slope c in the xy plane. Okay, and so so you can write the equation, right? So the equation for this, for such curves, are as follows, right? That y minus y0 is equal to c x minus x0. Okay, so if you have an initial point x0, y0 is in that curve, it's like, and you want to find a slope of, you want to find a line with slope c which goes through that point. This is the defining equation for that. Okay, so you might ask, what's the purpose of such characteristic curves? It's like, what does it buy you? So let's consider the following problem. So let's consider a slight extension of this. So again, you still have the same differential equation, that ux plus c uy is equal to 0. But let's just assume, in addition to that, that I've specified the initial condition for the x-axis. So I also have that ux comma 0 is equal to some function of just x. Okay? All right, so let's see what happens. So let's see where we are right now. Okay, so this is the xy plane, and I've said that I know what u along the x-axis is. Right, this is just f of x, and you also know that by this calculation that the solution u is constant along curves of slope c. Okay, so let's say this is slope c. Okay, and this is some initial point x0, y0, if you will. So you know that along the entire curve, right, that function value is constant. Okay, so at least in this case, it's like you have this nice, foliation. It's like of the entire domain xy by characteristic curves, right? So for any point which you could possibly want, there is a curve. There's a straight line. It's like of slope c which goes through it, and in particular, that line would then intersect this x-axis at a given point. Okay, so this is where things start getting useful. So if you know this initial condition, you know that these characteristic curves exist, then what happens then is that you can essentially backtrack from the point you want to evaluate the function at back along a characteristic curve. It's like until you hit the surface where the initial data is given to you. And then by the fact that the function value is constant along this characteristic curve, if you want to know what u is at this point, all I need to do is again backpropagate along this slope of this line of slope c back to this initial surface and evaluate f at that point. And that's going to be the same value as this point. Okay, so right. So the idea is that to find the value of u at xy, right, you find the straight line or the characteristic curve that goes through xy and see where that curve intersects the surface with the initial data. Right? Then the value of u at xy is given by the initial value or the initial data at this intersection point. Okay, so that's basically what is happening here. Okay. So let's see what happens, right? So let's just say x0, y0 is actually the point you want to evaluate it. Well, actually, x and y is where you want to evaluate it at, right? Okay. Okay, so let's try to evaluate u at x0, y0. All right, and I want to find a point x, it's like which is on the x-axis. Okay, so x being on the x-axis means that the corresponding y value is 0. So the defining equation for a slope of a line of slope c, right, is just that y minus y0 divided by x minus x0 is equal to c, but the y value corresponding to this x is 0. Okay, so I can solve for this. So that means that x is equal to x0 minus y0 over c. Okay. Okay, so this is minus y0 is equal to c x minus x0, right? So this implies that cx0 minus y0 is equal to cx, which implies that x is equal to x0 minus y0 over c, right, which is the equation I had here. Okay, all right, so this is the value of x corresponding to x to the intersection point, right, if you had started with a point x0, y0. So this is telling you, it's like by the fact that the solution is constant along characteristics, that u at x0, y0 is equal to u at x0 minus y0 over c, comma 0, right? But this is equal to f at that point, f at x0 minus y0 over c. Okay, so that's basically the idea. Okay, and so let's look at a slightly more complicated example where it's not just straight lines. Okay, but let's see, the basic idea is the same. So let's say you have ux, it's like plus y, uy is equal to 0, and u 0y. So now changing the boundary condition slightly, is equal to f of y. Right, so as before, it's like I want a defining equation which says that u is constant. Okay, so all right. Right, so you have u x, y of x as before, and you want it to be constant along this curve. Okay, so this is equal to ux plus uy dy dx. So this means that dy dx is equal to minus ux over uy. So now you can substitute the differential equation, and so this is equal to y. Okay, so dy dx is equal to y. So this is just the exponential, right? So we know that the solution, so the solution passing through the initial point x0, y0 is given by y of x is equal to y0 e to the x minus x0. Okay. All right. And then, as before, it's like you now have this characteristic curve, and you want to sort of intersect the set of points where you have initial data given to you. Okay, so the intersection of the characteristic curve going through x0, y0 with excuse me, the y-axis, where the data is given by the condition that x is equal to 0, right? So you have that y is equal to y0 e to the 0 minus x0, so this is equal to y0 e to the minus x. Okay, so then it's like u at x0, y0 is just given by f at this point, right, which is y0 e to the minus x, sorry, x0. Okay, so that's the solution in terms of the data which is given to you. Okay, so hopefully that gives you some idea of how this method of characteristics might apply at least to these sort of simple examples of differential equations. So more generally, of course, it's like you might not be able to, when you write down the characteristic equation, you may not be able to solve the, characteristic equation analytically, but that's fine, because then you can use some sort of numerical method to approximate the solution, and then still use the same basic idea to compute the solution of the PDE. So with that, let me just stop here for now.